Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll work out three numerical examples on uniformly tapered bar of circular cross section. The problem statement is find the change in length of a uniformly tapered bar of circular cross section which is 1.2 meter long due to an axial pull of 60 kN at its ends. The bar has 80 mm diameter at one end and 60 mm at the other end. Young's modulus E is 210 kN per mm square. Now P is 60 kN, 60 into 10 raised to 3. So it's a uniformly varying bar of circular cross section and it is subjected to an axial pull 60 kN at its ends. And it is 1.2 meter long and diameters changing from 80 mm to 60 mm and Young's modulus is given. So it's a direct application of the formula which you have studied. Directly you can apply. It's a uniformly tapered bar of circular cross section. It is subjected to an axial pull of 60 kN. So the load is 60 kN, 60 into 10 raised to 3 Newton. Length is 1.2 meter, 1200 mm. Diameter is 80 mm at one end. So we will take D1 as 80 and D2 as 60. You can interchange this. You can interchange it and take D1 as 60 and D2 as 80. That doesn't matter. That will not make any difference in your solution. E is 210 kilonewton per mm square. So kilo you can convert by multiplying by 10 raised to 3. So 210 into 10 raised to 3 Newton per mm square. So kilonewton per mm square is nothing but gigapascal. Now the formula for a uniformly tapered bar of circular cross section is for deformation or change in length is 4PL by pi d1 d2. So delta L you can calculate. P you can substitute 60 into 10 raised to 3. Length is 1200 mm. Young's modulus is 210 into 10 raised to 3. D1 and D2 80 and 60. So substituting you will get delta L as 0.0909 mm. So this is the deformation produced in the bar due to axial pull of 60 kN. Let us work out another example. Now in the figure a step bar is shown. A step bar is subjected to an external loading as shown in figure. Calculate the change in length of the bar. Take E is equal to 200 gigapascal for steel and E is equal to 70 gigapascal for aluminum and E is 100 gigapascal for copper. So there are three different materials: steel, aluminum and copper, and first portion is of uniform diameter and second portion is uniformly varying cross section and the last portion is uniform diameter, because diameter its first portion 25 is given, 20 mm diameter. Here it's 50 mm diameter. Length 300, 200 and 200. Now here this portion, here the diameter is 20. So this end is 20 mm diameter and here this portion is 50 mm diameter. So this end of the aluminum rod is 50 mm diameter. So the aluminum portion, the diameter is varying from 20 to 50 mm. Now all portions are subjected to same load because end axial pull is acting. Okay, so all steel is resisting the same load 40 kilonewton. Aluminum is also resisting the same load. Copper is also resisting the same load. So all portions are resisting the same load. Now steel portion you have to use PL by AE, copper portion you can use PL by AE, but aluminum portion you have to use 4PL divided by pi d1 d2 because it's a uniformly varying cross section. Now let us work out. The force in all the sections are same, 40 kilonewton, 40 into 10 raised to 3 Newton, it's Newton. Delta LS is PES. I have used the subscript S for steel, A for aluminum and C for copper. So you can write delta LS is PS LS divided by ASCS. P is 40 into 10 raised to 3. Length of that portion is 300. Area is, diameter is 20. So pi by 4 d square is the area. Young's modulus is 200 into 10 raised to 3 Newton per mm square. So it works out 0.191 mm. Now in the aluminum portion, you have to use 4PL divided by pi d1d2 formula. So I use the subscript A for aluminum. So 4 into P is 40 into 10 raised to 3. Length of that portion is 200 and Young's modulus for aluminum is 70 into 10 raised to 3 and diameters are 20 at one end, 50 at the other end. So it works out 0.1455 mm. And the copper portion, you have its uniform area of cross section. You can use PL by AE. Load is 40 into 10 raised to 3, length is 200, diameter is 50, so pi by 4 into 50 square. Young's modulus is 100 into 10 raised to 3 Newton per mm square. So it gives a deformation of 0.0407. You can observe all the loads are tensile, all are subjected to same load. So all these are positive deformation, that means elongation, and you can add up all the elongation which will give the total elongation as 0.3772 mm. Let us work out another example. A round bar with a stepped portion is subjected to forces as shown in figure. Determine the magnitude of force P such that the net deformation in the bar does not exceed 1 mm. Young's modulus of the material is 70 gigapascal. Big end diameter and small end diameter of the tapering bar are 40 mm and 12.5 mm respectively. So big end diameter and small end diameter of the tapering bar are 40 mm and 12.5 mm. So this is tapering portion. So the big end diameter is given 40 mm, small end diameter is 12.5 mm. And these are uniform cross section. Area is directly given 400 mm square, area of cross section, and this is area of cross section is 200 mm square. All portions lengths are given and the loads are given in terms of P. Okay, P can be 100 Newton, 200 Newton or whatever it is. You need to solve it. Question is to find out the magnitude of P so that there will be a total elongation of 1 mm. So 1 mm is the total elongation. The elongation should not exceed 1 mm. So you are finding out the minimum force P that should be applied. So once you know the P, you can find out 2P, 3P, 4P. Okay. So if you get 100, this 2P is 200, here it is 300 Newton and here it is 400 Newton. So material is same, Young's modulus is 70 gigapascal. Okay. So but here the forces in each sections are different. So we need to find out the forces induced in each section. So the method is just take a section, consider the portion right side and sum up the forces on right side. So if you take a section here, the internal force is 3P. If you take a section here, internal force is considering that right portion, section plane is passed here, considering the right portion you have two forces, minus P and plus 3P. So you get 2P. In this, if you take a section minus P plus 3P, you get 2P. Here, if you take a section here, three forces are acting right side, 2P minus P plus 3P, you get 4P plus 4P. So first portion plus 4P, second portion plus 2P and last portion plus 3P. So you are getting the forces in all the three sections. So you can find out the forces. F1, first force in the first section, 2P minus P plus 3P, 4P you get. Force in the second section is minus P plus 3P, you get 2P, and force in the last section is plus 3P, as I explained earlier. And the total change in length is 1 mm. So you can separately find out delta L1. Delta L1 is 4 because first portion is uniformly tapered portion. You have to use 4PL divided by pi e d1 d2. P1 is that is force in the first section equation. I have used F1. So F1 is nothing but the force in the first section, which is 4P. So P1 is 4P and length is 600 and Young's modulus is 70 into 10 raised to 3. D1 and D2 are 40 and 12.5. So force, internal force is 4P. You don't substitute P, 4P. 4P is the internal force. So substitute that, you will get in terms of P. So the deformation you are getting in terms of P, 8.731 into 10 raised to minus 5 P. Next two portions are uniform area of cross section. So delta L2 is P2 L2 divided by A2 E2. P2 is force in the second section is 2P. So 2P you can substitute. Force in the second section is 2P and length is 700, area is 400 and Young's modulus is 70 into 10 raised to 3, which gives 5 into 10 raised to minus 5P. Delta L3 is P3 L3 by A3 E3. Force in the third section is F, okay, 3P. 3P you can substitute into length 500, area 200. Directly area of cross section is given and Young's modulus is also known. You get 10.7143 into 10 raised to minus 5P. So these are the deformations. You are getting the deformation in terms of P. Add all the three deformation which will give the total deformation. So total deformation delta L is delta L1 plus delta L2 plus delta L3 and we know that delta L is 1. It should not exceed 1 mm. So delta L is 1 mm. Add all the three values which you got for deformation, all in terms of P. You will get again in terms of P. Right side will be in terms of P. You can solve for P. 1 divided by this. So you get 4090.766 Newton or 4.09 kilonewton. So this is the value of P. P is 4.09 kilonewton. So 2P is going to be 8.18 kilonewton. Like you can find out 3P and 4P. So this is the magnitude of P that should be applied on the bar to get a 1 mm elongation. More than this, if you apply, the elongation will go beyond 1 mm. This is a maximum force you can apply, maximum value of P, which will restrict the deformation to 1 mm. That's all for today. Thank you for watching.